So, we shall now consider the case when the given function f of x is approximated by a quadratic polynomial, which we denote by p2 of x. So, our theorem tells us that f of x minus p2 of x is equal to n plus 1th derivative. What is n plus 1 in this case? How many points should be given to you? Information at 3 points are required, so that we can represent the function by a polynomial of degree 2, which is p2. So, f of x minus p2 of x is the n plus 1th derivative, that is the third derivative at some psi divided by n plus 1 factorial into pi n plus 1 of x. What is pi 3 of x? It is x minus x naught into x minus x1 into x minus x2. So, information is given at x naught f of x naught, x1 f of x1 and x2 f of x2. So, this psi belongs to the interval x naught to x2. And what is p2 of x? p2 of x is the quadratic Lagrange interpolating polynomial that interpolates the function at the set of discrete points x naught, x1, x2. And what do you know about x naught, x1, x2? x naught, x1, x2 are equally spaced. So, we are determining the error bound in case the interpolation points are equally spaced. So, in this case I shall take my x1 to be such that, or x1 minus x naught is h, x2 minus x1 is h. So, any x I take this to be x1 plus RH. So, when r is minus 1, what do I get? X is x1 minus h, and what is it? That is x naught. So, I am at x naught. Whereas, when r is 0, my x is at x1, and r is 1, my x is x1 plus h, and that is x2. So, as x runs between x naught and x2, my r runs between minus 1 and plus 1. So, I shall write down this pi 3 of x as, what is pi 3 of x? It is x minus x naught. What is x? X is x1 minus h, or x is x1 plus RH minus x naught, then x minus x1. So, x minus x1 is RH. So, I shall directly write down that, and then I have x minus x2. So, what is x2? x2 is x1 plus h. So, x is x1 plus RH minus x2, which is x1 plus h. So, this gives me x1 minus x naught, which is h. So, h plus RH into RH into x1 gets cancelled. So, I have RH minus h. So, taking the factor h from each of these, I have h cubed into r plus 1 into r minus 1. So, h cubed into r square minus 1, and that is pi 3 of x. So, I shall write this as h cubed into phi of r. What is phi of r? Phi of r is r into r square minus 1, and r runs between minus 1 and plus 1. So, R is such that it ranges between -1 and +1. So, now let us look at the properties of phi of r. When we know the properties of phi of r, from here we can get some information about phi 3 of x, and that will help us in finding the error bound. Because what is the error bound? Modulus of f of x minus p2 of x is the maximum value of third derivative of f at psi in the interval x0 to x2 by 3 factorial into modulus of pi 3 of x. What is modulus of pi 3 of x? It is h cubed into modulus of phi of r. So, we require the properties of phi of r. What is phi of r? It is r into r square minus 1. So, let us find out phi dashed of r. So, phi dashed of r will be 3 r square minus 1, and it vanishes when r square is 1 by 3, or it vanishes when r is equal to plus or minus 1 by root 3. So, now let us see what happens when r square is less than 1 by 3. When r square is less than 1 by 3, then here when r square is less than 1 by 3, we have phi dashed of r to be negative. On the other hand, when r square is greater than 1 by 3, phi dashed of r is going to be greater than 0. So, this tells us that phi decreases in the interval minus 1 by root 3 to plus 1 by root 3, and this tells us that phi increases in the interval minus infinity to minus 1 by root 3 and 1 by root 3 to infinity. Phi double dashed of r is going to be 6 r. So, at r is equal to plus 1 by root 3, phi double dashed of r is positive, and at r minus 1 by root 3, phi double dashed of r is negative. Therefore, phi attains minimum at r equal to 1 by root 3 and attains a maximum at r is equal to minus 1 by root 3, and it decreases between minus 1 by root 3 to plus 1 by root 3, and on minus infinity to minus 1 by root 3 and 1 by root 3 to infinity, it increases. So, the graph of this function is such that, and phi of r is 0 at r is equal to 0. So, at r is equal to minus 1 by root 3, it attains a maximum, and at r is equal to plus 1 by root 3, it attains a minimum. In this interval between minus 1 by root 3 to plus 1 by root 3, it decreases, and beyond this it increases, and therefore, the maximum of phi is attained at this point. So, we compute the maximum value of phi, which is attained at r is equal to minus 1 by root 3. So, maximum of modulus of phi of r for r lying between minus 1 and 1 is going to be maximum of modulus of r into r square minus 1. So, r is minus 1 by root 3, r square is 1 by 3 minus 1. So, that gives you 2 by 3 root 3. So, when I know maximum of modulus of phi of r, I can write down what is the maximum of phi 3 of x when x runs between x naught and x 2. So, it is going to be h cubed into 2 by 3 root 3. So, we shall make use of this here and obtain the error bound in quadratic interpolation. So, let us work out the result here. So, modulus of f of x minus p 2 of x therefore, is less than or equal to m 3. What is m 3? Modulus of the third derivative of f is less than or equal to m 3 for psi in the interval x naught to x 2. So, m 3 by 3 factorial, that is 6 into maximum of pi 3 of x. Pi 3 of x is h cubed into phi of r, and we have the result here. So, that gives you h cubed into 2 by 3 root 3. So, this is h cubed into m 3 divided by 9 root 3. So, the error bound in quadratic interpolation is such that modulus of f of x minus p 2 of x is less than or equal to h cubed into m 3 by 9 root 3. So, this gives you the size of the bound on the error when you approximate a function f of x by a quadratic interpolating polynomial. So, we shall again illustrate this result by means of the following example. Let us consider this example. The question is, obtain the step size h that can be used to tabulate the values of the function f of x is equal to sin x in the interval 0 to pi by 4 at equally spaced nodal points, so that the error of the quadratic interpolation is less than 5 into 10 to the minus 8. So, let us take the 3 equally spaced points to be x I minus 1, x I plus 1 be the 3 equally spaced points. Which we want to choose from the table of values of sin x, and then interpolate the function sin x by a quadratic polynomial that interpolates the function at a set of these 3 points. We have already computed the size of the bound on error, namely modulus of f of x minus p 2 of x is less than or equal to h cubed into m 3 divided by 9 root 3. So, now I want to find out the step size h such that x I is x I minus 1 plus h, x I plus 1 is x I plus h. So, that I satisfy the requirement given in the problem. So, I require m 3, and that is the third derivative of sin x in absolute value, and that will be less than or equal to 1 in the interval 0 to pi by 4. That is clear. So, m 3 can be determined, and that is the maximum of modulus of f triple dash of psi for psi in the interval 0 to pi by 4. So, the first derivative is cos x, second derivative minus sin x, the third derivative is minus cos x, and the maximum of that in this interval is going to be 1. So, m 3 is known. So, I want h cubed by 9 root 3 into 1 to be less than or equal to what? 5 into 10 to the minus 8. So, h cubed must be less than or equal to 45 root 3 into 10 to the minus 8. And if you evaluate h, and that turns out to be approximately 0.009. So, I shall give you another problem and you can try to work them out in the as a homework. Suppose f of x is equal to x square into log x. The question again is determine the step size that can be used in the tabulation of this function in which interval? In the interval 5 to 10 at equally spaced nodal points, so that the error in quadratic interpolation can be less than 0.00005. That is what the question is. So, maybe we can work out the details quickly, so that is another example that illustrates our result, and I can give you more problems similar to this in the assignment sheet. So, what do we want? We require f dashed of x, that will be 2x into log x plus x square into 1 by x. So, it is 2x log x plus x. We require f double dashed of x. So, it is 2 into x into 1 by x plus log x into derivative of x plus 1. So, it is 2 into 1 plus log x plus 1. So, it is 3 plus 2 log x, and I also require the third derivative because I want m3. So, that will give you 2 by x. Where does x belong to? X belongs to the interval 5 to 10. And what do I want? I want m3, which is maximum of modulus of f triple dashed at psi, for psi in the interval 5 to 10. So, we require maximum of modulus of 2 by x for x lying in the interval say 5 to 10. Since f triple dashed at psi, I can write this as psi and this also as psi. So, what is the maximum? Where is it attained? The maximum is attained at the lower limit. So, it is 2 by 5. So, we can now use the inequality for the error bound and write down that modulus of f of x minus this quadratic polynomial is less than or equal to h cubed into m3 by 9 root 3. This is h cubed into m3 is 2 by 5 9 root 3. And what do I want? I want 2h cubed by 45 into root 3 to be less than or equal to 0.00005, and that gives h to be approximately 0.0580. So, if you take the step size h to be such that h is approximately 0.058 and choose 3 points xi minus 1, xi plus 1, which are equally spaced such that xi is xi minus 1 plus this h. Xi plus 1 is xi plus this h. Then if you approximate this function x square log x in this interval by a quadratic interpolating polynomial, the error cannot be greater than this value. That is what the result says. So, summarizing what we have done in this class, we obtained the error in interpolation and then obtained the error bounds for the cases when we approximate f of x by a constant polynomial, a linear polynomial or a quadratic polynomial for the cases when the interpolation points are equally spaced. We derived the Lagrange interpolation polynomial for points which need not be equally spaced, and also obtained the expression for error in interpolation for that case, and then obtained the error bound for the special cases when the points are equally spaced. We shall continue with another way of developing interpolation polynomials when the points are not equally spaced, and we use the concept of divided differences, and we shall consider this in the next class.